Hey everybody, let's move on to Unit 4, transformations. So we've learned how to draw things, we've learned how to rasterize them, get them on the screen. But as you've seen, it's a lot of work to get your geometry in your assignment. You've seen it's a lot of work to get your geometry to draw it correctly. So what if you wanted to take your sphere and draw it somewhere else? Stretch it, or if you have an object that you've come up with and you want to rotate it. So ideally, we don't want to have to remake our drawings every time we want to draw it differently. Ideally, we want to take existing code right, some object that you've created, like a teapot, and apply a transformation and draw that. Okay. We don't want to recreate the geometry. We've already solved that problem. We don't want to have to recreate the geometry for each variation. And so we need to perform standardized transformations. We need some standardized transformations to let us do this. And I'm going to come back to this, but the basic ones, we want to rotate. We want to resize. We want to move it, right? All those kinds of things. So I'm going to do a quick demo. So here's some processing code. Don't worry about the code. We'll come back to that later and we'll learn all about it. So here's an object we've come up with, an hourglass shape, and it's drawn based off of this coordinate system. That's kind of nice. But what if I want to draw it somewhere else, like over here? So we want to draw it over here in a different coordinate system or rotated. I shouldn't have to go through and have to solve all those points again. I should be able to just say rotate it. I've already given you a shape. Scale it down a little bit and rotate it. Or even if it's non-uniform, what if I want to stretch it in funny ways? I want to be able to do this without recreating the original object. I want to be able to transform it so that I can solve it once and then use it in many different places. Okay. So the basic idea that people come up with for transformations, the naive solution is, let's just do each transformation in standard code. Okay. I could teach you how to do that. You could figure out most of them. It's not a big deal. So that's the naive approach. So for example, let's work through some examples. Move. If you want to draw somewhere else, right? Then we just calculate the new point is going to be the old point plus some offset. Right? Move it minus 10, move it plus 1, those kinds of things. If I want to rescale, make it bigger, make it smaller, I can say, well, I want to take each point and I'm going to multiply it by some scale factor x, so things move away from the origin in a uniform fashion. I can scale it up. We could do the same thing with rotate and all the other ones. We can solve, how do we modify these points anyway? And if you look at my code for assignment 1, you'll see the rotation code kind of just does this. It just, we know how these works. We can implement this in standard code. But there are some problems here. The biggest one is that it just doesn't scale well. As you'll see as we work through this unit, it doesn't support, hold on, my silly note program. It doesn't support combining transformations very well or undoing them, reversing them, right? It doesn't support any of that. So how can I combine? I suppose this should be capital. How do I combine operations? Right? Right now, I just do them in order. I can rotate, then I can translate, I can do all that, those kinds of things. How do we do the inverse? How do we undo something? I suppose we is better, but it doesn't matter. We do the inverse. Okay, how do we work backwards? You have to solve it for each case. And you still can't combine them. So you basically had to handle everything separately. There's a lot of special cases. And there are no shortcuts. So this simple approach is cumbersome and does not scale. Does not. So if you look at the sample solution from the old assignment, you will see in there that my approach there is using this classic. It just doesn't work very well. Okay, let's see if I can get this note program to respond. Of course it doesn't. There we go. What am I supposed to say next? I'm lost without my notes. How can I ever do it? Okay. So there's a better way. There's a better way to do it than just coding in all these translations. And we've already seen a lot of this throughout the course, but now let's really formalize it. The idea is, you know, these kinds of problems, applying transformations, changing coordinate systems, vectors, points, we have a math system for that, and it's called linear algebra. Now, linear algebra is awesome, and you'll see how useful it is as we work through this unit for graphics. But to get started, it already deals with coordinate systems. Right? And we have vector spaces, we have vectors, we have points. You're already learning cross product, dot product. Of course it all fits together. We didn't just choose this is natural. It's the same class of problems. It just makes sense. And so if we look to linear algebra, then what we end up wanting to do is, if we represent our transformations as matrices, we can solve a lot of our problems. If we represent transformations as matrices, those above problems, a lot of them go away. So things get much easier. So a lot of what we're going to learn in this unit is how do we represent those obvious things that we want to do, like translation. Let's just add some to our point. That's easy. How do we use that in linear algebra? It's non-trivial, okay? It can be non-obvious. And I've actually said this earlier in the course, but I want to bring it up again now because it's going to be really relevant. There are two systems we can use here, and both are valid, okay? We can use the point as a row vector. So I can do something like this. Here's my x, here's my y, and then I want to multiply it by some matrix, right? Matrix. These are just variables in here, doesn't really matter. And then that'll give me, if I multiply that out, I'll get a new point, x prime, or I should call it x translated, y translated, right? So I can take my row vector, multiply it by a transform, and get a new point. We can also do it with the point as a column. And this is more popular. Okay? So I can do so you should remember your matrix multiplication, that the size of the matrices coming in determines the size of the matrix coming out. So if I have a row vector, I pre-multiply the vector into the matrix to get the vector back out. And for the column, we do it the opposite way. M1, M2, M3, M4, XY. And this is going to be my new X that's transformed and my Y that's transformed. Yeah, so this later one is more common, and it's what we're going to use. Column is more common. And I'm going to come back to this throughout this unit, but this is really important, the order, okay? With the column vector, you put the vector at the end and you apply the matrix in front of it. The order matters, but we'll come back to that. So if we use linear algebra, there's a lot of really cool things that we get, okay? And I want to talk about a few of them. So the first thing we can do is we can combine transformations really nicely. And let me show you how this lends to pre-computing. So remember, we haven't figured out exactly how to do it yet, but if we can make our transformations into matrices, then we can do the following. I should highlight this. We can combine. Okay. So let's say I have a transformation, and I'm going to write them in this order. I'm going to put, let's say I have a transformation 1, transformation 2, transformation 3. Okay, I have these 3 transformations. Let's say that this is a translate. So translate means move location. Let's say that this is a scale, so resize, and let's say this is a rotate. What's really cool is I can pre-calculate, I can multiply those together. They're just matrices. If these are both all 3 of these are 2 by 2 matrices, I multiply them together, I get a new 2 by 2 matrices. So I can calculate matrix combined, and I just multiply those together, M3, M2, M1, and it'll be the same. So this matrix combined will have the same effect as those 3 matrices put together. So then I can just do this matrix combined multiplied by my vertex, which is going to give me the same result as M3, M2, M1V. So previously I had to do translate, rotate, I had to do everything separately with my functions. Now, if I know what I want to do, I can come up with the matrices for them. I can come up with the matrices for them, pre-compute them, combine them into a combined... oh, you gotta be kidding me. Oh, good. My screen glitched, and I thought the whole time you couldn't see my sketch, and I had to go redo this lecture. Good thing I didn't swear. All right, so you don't have to be kidding me. I'm just going to blame my screen. Let's continue. Where was I? Whew, that scared me. Matrix combined. Yes, our matrix combined. We pre-compute those things. Now I have this one matrix that will transform my vertex the way that I want. So I want to talk about this real quick. So note the reverse order. So I put M1 on the front, and the reason for this is right there. Because the vector comes at the end, right? So what's going to happen first is it's going to apply M1 first. So in this case, it's going to rotate first. After the rotation, then it'll do the scale. After the scale, then it'll do the translate. Okay? You need to be very careful with that order, and I'm going to give some examples. After we learn our transformations, I'm going to give some examples of why that really matters. But the reverse order trips people up. It'll do them in reverse order because of what I've just shown here. So I'm going to keep coming back to that, okay? File that away. That's the spot that trips people up. Another thing we can do with matrices is we can do inverse operations. This is really cool. So if I have my MC, my matrix combined, and well, I know I can do that, and I apply it to my vector to get a new vector, but all I need to do is calculate the inverse of that matrix. If I can invert that matrix, I multiply it back, and I can undo whatever operation I get. So here you see I translate V using my combined matrix. I change my mind, I can translate back. And that might seem like a weird thing we need to do right now, but sometimes you're like, I can do the transformation to go all the way to my screen space, but what if I want to go back into the world space? I want to work in the opposite direction to see where is this within my item, that kind of thing. So we can go in both directions just by coming up with that inverse. And again, careful with the inverse order. Okay, because of the way that it works. So if I do M, I'm going to write this backwards just to avoid confusion. If I have a point and I first apply matrix 1, and then I apply matrix 2, and then I apply matrix 3, I'm going to get point prime. To undo that, I need to put them in reverse order. If I have point prime, because M3 happened last, I need to do that first. So invert of 3. So I applied 1, then 2, then 3. If I want to undo it, undo 3, undo 2, undo 1. I did 1, I did 2, I did 3, undo 3, undo 2, undo 1. I repeated myself because it's that important. So first I undo 3. Oops, that's a 2. Then I undo 2, and then I undo 1. And then I'll give my point back. So just be careful about that. All right, I'm going to stop here and come back, and we'll learn a little bit more about these, about using linear algebra for doing our graphics.